Hello, welcome back to iRender tutorial series. Today, we're excited to bring you a brand new tutorial on Fibonacci lattices, a fascinating technique used to create beautifully even point distributions in 3D space. Fibonacci, also known as Fibonacci, was an Italian mathematician widely regarded as the most talented Western mathematician of the Middle Ages. When mentioning him, we think of the Fibonacci sequence and the legendary golden ratio. The Fibonacci sequence is not only a fundamental concept in mathematics, but also appears extensively in life, and especially in nature. The Fibonacci sequence and the golden ratio are closely related to a botanical phenomenon known as phyllotaxis. In botany, phyllotaxis, or phyllotaxy, refers to the arrangement of leaves around a plant's stem. This arrangement often forms spiral patterns, a striking and recurring motif in nature. Many plant species exhibit this spiral pattern, and it is believed to play a key role in maximizing sunlight exposure and optimizing space for growth. Interestingly, these spirals are often aligned with the Fibonacci sequence and the golden ratio. For instance, the divergence angle between two successive leaves is typically around 137.5 degrees, which corresponds closely to the golden angle derived from the golden ratio, approximately 1.618. Today, we'll recreate this beautiful natural pattern by building a Fibonacci grid simulation using the Scene Node system in C4D. Let's get started. We'll begin by creating an object group and entering the Scene Node's environment. I'd like to thank Maxon developers for creating a spiral distribution node for us to make things easier. This node lets us control key parameters such as the number of points, the rotation angle, and the scaling factor, giving us full control over how the spiral develops. Next, we add a decompose container node to break down the output of the spiral distribution into usable data. We call the iterate collection node to extract the necessary data and connect it to the matrix port. We can check the display by using the points to line node. Set the mode to values and adjust the scale parameter to y equals 0 cm so that all the points lie flat on a plane. And just like that, we have the phyllotaxis pattern. For better visualization, we can take it a step further by using the transform geometry node and instancing a sphere onto each point. This gives us a clear spiral structure. Feel free to tweak the parameters, such as count, angle, and scale, until you're satisfied with the look. And there you have it, a completed simulation of phyllotaxis on a flat plate. First, we'll start by using the fill array node and enabling the length port to define how many points we want to generate. Next, we use the iterate collection to collect the necessary data. From here, we extract two key values, count and index. Then, we regroup everything into the initial point set. Now, this next part gets a bit mathematical, and to be honest, I'm not a mathematician, but I came across a helpful discussion on Stack Overflow, where someone broke down the math behind Fibonacci lattices on a sphere. It's a great read if you're curious about the details. In summary, when we need to allocate n number of points with Fibonacci lattices, assuming on a unit sphere with r equals 1, we will have a y equals 1-2, index /n1, with y from -1 to 1. Radius y equals sqrt, 1y squared. The radius of the disk formed by the cross-section of the unit sphere, and an xz plane sliding down the y-axis between 1 and -1. Angle theta equals in x asterisk angle of divergence phi. Angle of divergence, according to the Golden ratio, is approximately 137.5 degrees. X equals cos theta asterisk re. Z equals sin theta asterisk re. Now back to the node space. We will use the arithmetic nodes to find the x, y, z values. Create the u parameter to control the y displacement. Use the power and root nodes to determine re. Use the trigonometry nodes to determine x and z. After having x, y, x, we use the compose vector 3D to integrate them. Next, use the scale node to control the sphere R. Connect to the transform geometry node to display the results. You can readjust the U parameter to get an accurate and proportional distribution. You can create a sphere with a smaller radius so that the display results are more recognizable. We have seeds attached to the sphere. Don't forget to adjust the parameters to check. We can add color to the seeds by using the basic gradient node with the position port to get the result of the Y parameter. Then pass that into a color operator node to apply color to each seed. Now you can play around with the parameters until everything looks just right. To simulate phyllotaxy over surface of revolution, we do the same. Some node and parameters need to be adjusted. We use the base spline rotated around the y-axis to create the surface. In this case, y will remain the same value, and the radius will be equal to the absolute value of x. When we modify the base spline or use other base lines, we will get different surfaces and also get different phyllotaxy patterns. Adjust the parameters until satisfied. And that wraps up our tutorial on simulating Fibonacci arrangements using the scene node system in Cinema 4D. We hope you found this walkthrough helpful and inspiring for your own creative experiments. If you enjoyed the video, don't forget to like, subscribe, and stay updated with more tutorials coming your way. Thanks for watching, and as always, happy rendering, happy creating with iRender.